also click on the quantum information theory too. And I want to use the opportunity to speak in front of you today to present like some work that we call like local simplification of many-body steady states. And the idea of this work is to try to use this kind of like relaxation or like convex optimization methods that Tony introduced this morning to be able to say something about open quantum many-body systems. So systems that are made up of many quantum particles that interact in an environment. And this work is published in the archive at the moment under this if someone wants to check it, and it's in a collaboration with Tony, who's the head of the quantum information theory. So let me present the plan of the talk. So first, I will introduce the many-body problem in quantum mechanics. That is just a bit that I will introduce again. And I will present like this family of like relaxation, convex relaxation or simplification methods. And then lastly, I will introduce, or like what I will present this application that we introduced to describe open quantum systems. So let me present like first this family of methods, which are sometimes called like convex relaxation. So the idea is that if we want to describe like a many-body quantum system, we have this close dimensionality of the relevant space. No? If you want to describe exactly an arbitrary state of a many-body system, you have to give me an exponential number of parameters to describe the state. And of course, like this doesn't make things you cannot do it exactly, you can just like a few functions. So like traditionally, a very, let's say, like successful approach has been constructing like clever variation states. No? And these are sort of like approximations for like families of states that live inside this set of like states below. But they are constructed in such a way that they can be manipulated efficiently and with optimizations. And then the thing that people do is like, okay, they construct this family and they try to optimize let's say inside this set to find the best representation of like some state of this element. So maybe the graph. And I will introduce like this sort of like different approach where you use sort of like the outside approximations to the set of quantum states. And the idea is that in this way you sort of like obtain outside bounds or obtain equal bounds to the expectation values in the short quantum systems. And let me present a very simple example of a relaxation in quantum many-body. So imagine I have like some let's say like state of a let's say two-dimensional system. So I have like square lattice and I have two-level systems. System in particular. So to describe exactly like the full state, I would need to give you like the sort of like entire density matrix of the system, but we discussed this already. This was like exponential graph something. So something that is true is that if like for any sort of like quantum state of the global system, this state will have like valid different matrices. So if I single out, let's say like these two pairs of like qubits, this over there, this over there, and this over there, like, and I compute like from the global state that is matrices, like I will have valid different matrices. So that means that they will be described by some positive operator, which will be normalized as well, and they will agree to collect in the region for the other. But if you give me some set of resistance matrices for decision, the implication doesn't go in the other direction. So maybe you can give me a set of valid resistance matrices, so they are positive, they are normalized, and they agree in the regions where these regions overlap, but there's no global state rho compatible with these resistance. So in a sense, this is a relaxation. No? For every possible state, I can give these resistance matrices, but not the other way around. And in this way as well, like this, like the set of resistance matrices is more manageable. So I don't need to give an exponential number of parameters to describe. And then an example of like something that you can do with this, which is well known many years ago, is imagine you have like a Hamiltonian like sum of like pairwise terms. No? For example, like the terms that tells me how qubit I and J interact. So if I'm interested in computing the graph energy, this is just minimizing the expectation value of the energy over the set of like possible quantum many-body states. But because the energy is just like sort of like a pairwise function, so it's just a function of like the resistance matrices of let's say qubits I and J or I and J. So then I can write this minimization as just like minimizing the expectation value of the energy, which just depends on these resistance matrices. We understand that these resistance matrices have come from a global state. So here I found nothing. But if I forget about this global compatibility constraint, what I get naturally is a lower bound. So because I'm minimizing over life, so I forget about this compatibility constraint. And this is something that's called the Anderson bounds, and it's quite old. But yeah, it's an example of what you can do with kind of relaxation methods. Is figured out. And naturally, you get sort of like this picture that Tony was discussed this morning, where let's say, from the inside approximation, I get an upper bound to the energy, and from the outside approximation, I get a lower bound to the energy. So, well, this is all very well, but the idea is can use this for some other states can improve. So let me present, well, very quickly, like everyone's probably an expert on this, but just to, let's say, put everyone in the same page, let me present like a technical median of methods, which is a median programming, which is just an optimization problem where I have a matrix with like, let's say, a variable x, which is the variable of the optimization problem, which is constrained to be positive and satisfied by some linear constraint. And the nice thing about these median programs is that they are convex. So I find the local maxima, a local maxima, and a global maximum. And they are sort of all in practice, meaning that I specialize numerical solvers, that if I throw them, I throw a density to them, they will give me, let's say, the solution with like some guarantees. So, I mean, here I draw like, let's say, a very simple form, but you can sort of like adapt and you can have like multiple different frames, you can have maximization, minimization, because one. And as we will see, like this anything turns out like a two-step median of like this complex fluctuation method. So let me present like the sort of like the particular scenario where we apply this method, which is open quantum many-mode system. So an open quantum many-mode system is a system that interacts with an environment. So it cannot be described just by like some equation that involves the system. And in general, like the sort of like interaction between the system and the environment can be very complex, but in some cases we can describe effectively the evolution of the system by something that's called a master equation or a linearity. So what this means is that, let's say, imagine if this many-body system is just like a chain of two-level systems, I will have a Hamiltonian that sort of like tells me how immediate neighbor QTs interact, these extents and returns, and then I will have like this P, which is like some super operator that acts on the state that tells me sort of like models the interaction of the, like the effect of interaction in the environment in the system. So what this master equation will tell me is just it will describe the evolution of the system. So if I'm interested in how the system evolves with time, this is like the evolution is dictated by this linear operator that just acts as the usual Schrodinger equation with the Hamiltonian plus the effect of the interaction between the system and the environment. And there's one property about steady state that is relevant, that is that they useful, like they at least have like something that is called a steady state. So what it means is that if I start, and like usually for a many-body system, like these steady states are unique. So what this means is that if there's like at least one frame that doesn't evolve under the dynamics of the gradient, and if I start the system in an arbitrary state, and the steady state is unique, the system will converge to it. So if I leave the system for long times, I will find a long time steady state. And yeah, furthermore, like the convergence to the steady state is exponential. So we say it's described like the long-term time properties of the state. No? And the goal of our method will be to compute properties, or like to come up with a classical method that computes properties of the steady state. But the problem to sort of like solve this classically is that rho is a exponentially large object, and the invariant is a superoperator, so it's an even bigger exponentially large matrix. And I just have this to solve like this sort of equation. So I have to find a positive operator, which is on the kernel of this invariant, that this invariant is an exponentially large object, and in general it's a hard question. But so let me argue that some of the constraints that characterize these steady states can be written locally. So I said before that the definition of these steady states is that they don't evolve under dynamics. So if I compute in particular, I look at some expectation value, AI, in this steady state process, and I look at the time derivative of this, let's say, expectation value of time, because the steady state doesn't evolve, it should be zero. But if I use sort of like the equation of motion that I had before, the master equation, then I can see that this is just something that's called the adjoining invariant acting on this operator AI. And this is just some sort of like an expectation value of the steady state. The expectation value of the operator is given by the adjoining invariant acting on AI. So, and furthermore, if the system originally is local, so sorry, if like the original operator AI is a local operator, then the adjoining invariant acting on the operator of the original operator is also a local operator that we can access for. So that means that the AI was whatever, sigma set in this period and sigma set in this other one, then the action of the adjoining line on the entire system is just a larger operation. So it can be sort of like evaluated if we know something about the local information. So in this idea, let me present a relaxation for competing properties by competing expectation values of the steady state. So as a, let's say, like simplifying assumption, let's first consider a one-dimensional system. So, yeah, chain of like two levels. And then instead of like describing the entire state, which I said that it was exponentially cosmic, let me just consider rho k, which is a set of all the distance matrices of like k meter-stable particles. And as an like even let's say more simplifying assumption, like we can take a system with translation invariance, and then if the steady state is unique, for instance, like the rho k will also like all the density matrices will be the same. So let me write down like the following SDP, let's say, to sort of like compute bounds in these properties of the steady state. So imagine I'm interested in the expectation value of operator of the O, and then I have this SDP where I either maximize or minimize as a function of the density matrix, the expectation value of this operator O. And the constraints that we have are just imposing that this state is a valid state, so it's positive and it's normalized. Furthermore, I have a constraint that basically tells me that because rho k describes all the resistance limits of like k means neighbor in my system, that they have to be compatible with themselves, or let's say this is related to translation invariance. And then I have this constraint that basically tells me that the expectation values that whose time derivative, or let's say whose evolution I can compute from these resistance matrices, like should not evolve. So then this has the form of a semi-definite program because it's just a linear function, so a linear cross function in this matrix, a positive constraint and just linear. And well, yeah. So I presented this in this sort of like one-dimensional case, but for like general like non-translation by systems, if you have resistance matrices for all k regions, size k regions of the lattice, or you can also do it in like higher dimensions, provided like say density matrices, the distance matrices of different size. And finally, like the resulting problem does not depend, like you look at the problem, it does not depend on the system size. So what it means that the bound that we get, like the maximum and the minimum that we get for the expectation value O, the other ones, the lower bounds, do not depend on sort of like the original size of the system, so they are valid for all system size. And in particular, they also valid for systems in the y systems, which are very large. So let me present sort of like the results that we can get. So let me introduce briefly like the model, so we consider like a one-dimensional chain, which is simple model, but we sort of like take the fixed couplings of the systems and so that we have an trivial steady state, that there's no trivial correlations in the steady state. And then we can write down the previous SDP, like put it in our computer, and slowly as a function of like the size of these resistance matrices. And we can check at sort of like the performance of the bounds as a function of the size of the resistance. And then what we see is that, okay, if we put small resistance matrices, we get, say, quite loose bounds, but then the moment that we start increasing like, the size of the resistance matrices, like the, let's say, like upper and lower bounds of the expectation value sigma set converge quite fast. For the, let's say, largest systems, or like larger resistance matrix size that we simulate, we get bounds which are the order of like 10 to the minus 4. And this is for a many systems, so in general, this is something that is hard to compute, and these bounds are valid for systems of arbitrary size. And okay, this is not just something like a particular property of this expectation value, like if we put some other expectation value, we can also compute these kind of bounds. So, okay, let me jump and talk about the two-dimensional systems. So, as I said before, like you can generalize it provided that you sort of like take into account the connectivity of the two lattices. You can also consider two-dimensional systems with this method. And a little chance that we have is that because now, let's say, the interaction pattern of the invariance, like or of square lattice is larger, we have like a faster dose of the support of the operators to the adjoining invariant. So we want to impose that, let's say, like some operator with support in these 4 qubits is stationary, then we have to sort of like impose that, or like have as a variable the distance images of this size. But if you play a bit with the singletons of the model, you can also realize that, okay, like maybe you don't need sort of like such a large resistance image, like because let's say action of the action invariant on X is just a sum of like, let's say, operators that act on the original support of X plus one step unit. So with this, you can sort of like simplify a bit the complexity of the problem. And then you can sort of like look at two-dimensional systems. So I take something that we call like a short range or like square lattice version of the DP model, which is a model that has, let's say, so no interaction by Hamiltonian. So I just have like independent qubit oscillations in every qubit, but then the effect of the environment sort of like couples with the stable qubits, and in this correlations in the system. And then we can look at the, let's say, like performance of the bound, so like the, so that we get with our method as a function of the like size where we impose that expectation values. And what we see is that it's a bit hard to see these one by one, but if you look at sort of like larger regions, then you get bounds that sort of like converge very fast and give you update predictions for the expectation value of sigma y. So actually it's very easy to see, but here in every event dot there's an upper and a lower bound which are quite high. And this is the case for like let's say like all the expectation values that we can compute. And actually like you look at the difference between the upper bound and the lower bound for this kind of method, like you see that, let's say, for the entire phase diagram of this model, you are predicting, say, a couple of decimals of the local expectation values. So the difference is quite nice. So let me just, as a final example, to present an example of present results of like applying this kind of method to a model with a phase transition. So what this means is that, well, there's this two-dimensional Ising model, which is just, say, like, a model that is in the square lattice where I have like sigma set interaction between the neighbors, and I have a longitudinal field, and it's also subject to local dissipation. And the model has a dissipatory phase transition because there's like regime in this let's say linear space, like phase diagram, where the model has two steady states. And so like understanding, let's say, the properties of like these steady states, like a challenging problem, and for numerical tools. And yeah, for very good results that from this paper. And what they saw in this paper is that, let's say, like, there's like some vision where, yeah, so like the model has two steady states. So what we do actually in our paper is take, let's say, like, we fix a value of d over gamma of the other pair of 1, and then we scan length from left to right, let's say, in this parameter. And then what we see is that if we increase like the size of this region that we consider, for the larger sizes that we can consider, like we have sort of like bounds that collapse. The upper bound and the lower bound of this expectation value give us the same value. So sort of this is an indication that there shouldn't be two steady states in this particular area. But if we increase and sort of like go closer or like go to the thing where there's phase transition, what we see is that in some regime there is let's say like the upper bounds and the lower bounds do not collapse. So this sort of like indicates that the model has, or this is an indication that the model has two steady states, and then we're seeing the maximum expectation value over one of the steady states and over the other one. And if you go further in this regime where we have sympathic phase transition, like we see, say, for a larger range or value space. So with this, I conclude. So I presented this approach that like allows us to compute rigorously bounds on the local properties, local expectation values of steady states of open bound many body systems. And they have this nice property that you can understand them as, let's say, constant thermodynamic in electric systems, which are very large. And yeah, as I said before, like the results are in this paper. Yeah. So thank you very much for your attention.
Can you give some details about the semi-definite computations? Which solver do you use? Do you use complex numbers? What size of the problem do you use? Supercomputers or your laptop?
So that's a good question. So we use Mosaic. So at the end, like you have like one big, let's say, like matrix possibility constraint, and then you have like some linear constraints. And then, of course, like let's say, like the larger density that you use are your like.
But these are complex value coefficients.
Yeah. I mean,
We reformulate them with real coefficients.
yeah. So, I mean, sometimes I can say something. So, like, let's say that the better you implement like these methods, like the more clever you are, the better it is. So, like, there's one of these models, for instance, where you play with the local basis. You can write completely a stability problem, and then you can exploit these and get larger sizes. But yeah, generally complex numbers.
And you have sparsity with coefficients.
Yeah, so you have some sparsity, but we haven't explored so much, let's say. So I mean, that's like a line that we have to explore a bit more, like what's the best way to solve these systems. Because they have a lot of structure, but we're at the moment using like a black box. So,
how does the correlation length of the system end in this game? If you have a very large correlation length, we also need a very big margin. What is that not?
So yeah, like so for instance, like there's this exactly like this kind of model that we look, which is like a version of this I mean just like this Librarian. And then I think that have this transition like
Okay, but this model probably has a very, very short correlation length. This probably has a correlation length of 0.5 sites. So that's why.
Yeah, no,
but
like,
so the trick is always with these methods. How do they scale when you get close to some critical system? Or when you get a very large correlation length.
Yeah, no, like for sure. Like what I would say is that you can see that, like let's say in the two extreme, like if you put this to 0 or this to something very large, like the model has shorter correlation length and the bounds get better. In the intermediate regime, like the bounds, let's say, like grow, but still give you, let's say, like accurate results. But like so far,
but my question is there a correlation? It's like difficult. Is there like some inference about how does that bound scale as a function of correlation?
So I mean, like I find it very interesting, like doing so that we have interaction like this for this sympathetic model. But in general, like solving to the systems like with any other method, let's say like it's a challenging problem for the steady state. You know, like if I want to set up like some test computation to do these kind of things, like I would be careful. So yeah, but yeah, like I think it's a very interesting direction.
Can I ask?
Yeah.
So did you try to look into, let's say, what are you capturing when you truncate your the number of terms that you throw into the STP problem you try to solve, and what is that you're fixing and what is that you're not fixing? I will make you an example. Recently, we managed to understand a bit better how self-parameterization of quantum states to behave by looking at it's known as a Umlaut expansion. So, and you can see, for example, so it's a sum, you write your state at the sum of terms, that'll just the moment say, like expectation values of XX, NDCC, sorry, CCC, etc. Which look a lot like what you're doing here in a sense. So only have C terms. And did you try to understand a bit what is?
So like what we've seen, for instance, is that like the performance is better for the local expectation values. No? So you give these marginals out of the state, and then if I compute something that is like a single site expectation values, I get very tight bounds. But if I put in this marginal an operator that acts non-trivially in all the qubits, I would get looser bounds. No?
Okay, but for example, yeah, if you take x1, x2, or x1, x10, can you bound them well in the same way, or?
So like in principle, like you can run this as well, and like it would work. Like my expectation is that, let's say, like for nearest neighbor, the bounds are tighter.
Why?
So you have like more constraints, let's say, like so really like you're trying to exploit and impose like all the constraints that you can with these, let's say, marginal that you have, and they are more constraining for like stuff that is local, I would say.
And if you have bodies, if your error going exponentially with the number of bodies,
if I have what?
Look at x1, xxx correlations.
Like 3 on the qubits or something like this.
Yes.
Yeah, so like we've tried this a bit preliminary and we don't get like so good bounds. Not encouraging.
No, but it's interesting if it's exponential or polynomial or something. I would expect it exponential, but
Yeah, yeah, I mean, you have to do better.
I